Hello, welcome back to our little office chat here. And today we'll talk about a really new topic. We call it continuous wavelet transformations, but it's about wavelets. This is a subject which you probably have not seen in any other course, maybe not even heard about it in other courses, and I suspect may not see in any other courses as well until maybe graduate school. It's not a hard subject. It very much is a continuation of Fourier transforms to something modern, which hasn't been done before. So it's just excellent for computing. One of the things that is often missing in traditional curriculum is analysis that scientists use in the field. They use Fourier analysis, but not as much. They often use wavelet analysis, which we'll talk about today, and principal component analysis, which we'll get to later. So you'll do something new. And if you look up on the top here, you'll see that already we'll cover lots of topics because we'll build up to this gradually. And this first lecture on the basic wavelets will actually break up into two parts. First, we'll talk about the principles, because once you get an idea of what's going to happen and the full framework, then the mathematics is not hard. It's just basically accounting and simple trigonometry. So let's get on to that. But I wanted to show you also, I got my new camera here. It's very nice, and it's a digital camera. You know, it takes nice pictures. Ah, there you are. Wow, that's a picture of Sally. Let me show you the picture. That came out very nice. Pardon us.
Good.
Okay. Have you ever looked at a digital camera? One of the things you'll notice here, and I'll change this for a second. Okay. You notice, this was an image quality. This was normal image quality, but I can change that any way I want. There's normal, there's fine, extra fine, extra fine, that's studio quality, and then there's raw image. So it goes raw all the way down, high, extra fine, normal, basic. That's sort of for, the other kind of people, not us. And raw, which is the most intensive, data intensive. So, why am I showing you all this? Well, because I like my new camera, I like my toys. But also because this is a rare occasion in which some of the physics and the mathematics we'll talk about has this great practical value. So wavelets, in fact, are the basis of image storage on digital cameras. So let's talk about wavelets. So what do we see when we look at this slide? Well, we see three pretty colored boxes, and they're there, at this moment anyway, just to guide your eye. So we see a signal as a function of time that looks first like a pure sine wave, then like a more complicated couple of frequencies, who knows, beating, and then a much more complicated signal at the end in pink. So the question is, what frequency is present in this signal? Well, obviously, there's different frequencies present at each time. So what frequencies present at each time, and what frequencies are present at each time, because there's more than one. So we have both the number of frequencies present changing in time and their amplitudes possibly changing in time. So how do we do this? Well, we'll show you here an analysis which works perfectly well with numerical signals, and you can do that if you want, but actually I made this up with an analytic signal, and it's the functional form given here. So what we have here is a pure sine wave, frequency 2 pi for small time, combination of frequency 2 pi and 4 pi, but with different amplitudes, changing amplitudes in the intermediate time. And then at the last time period, the pink time period, we have frequency 2 pi, 4 pi, and 6 pi present. And again, with different amplitudes and amplitudes which change. So we're looking for some analysis that will tell us or show us visually that we have one signal at low times, two at middle times, three at higher times, and that the ratio of the different frequencies varies. Here 2 to 1, here, I don't know what that is, 2.5 to 6 to 10, some other combination, and get that information from the analysis. So how do we approach this? Well, the first thing you might do is look at the next slide. And the next slide shows that the first thing you might do is pull out your old friend, Fourier analysis and the discrete Fourier transform. Well, you can do that, but we did that here. This is our old friend, the sawtooth, where we have a periodic function going on for all time, and it has a spectrum for a transform that looks like this. And what we see is lots of components, but no idea about what time they're occurring. Well, here they're occurring for all possible times because the signal is repetitive. So that's the problem. Okay? The Fourier analysis was fine for what's called a stationary signal. In other words, a signal whose functional form is stationary in time. It may be a varying signal, but it doesn't change in form with time. But our problem's not like that. The form of the signal itself changes in time. Okay? So the problem with Fourier analysis is that these frequencies occur for all time. And if the signal doesn't, then it's not a good appropriate tool. And likewise, since the frequencies sine 1, sine 2 occur for all time, there's no time resolution possible with the tool. Furthermore, because all Fourier frequencies occur for all possible times, they're all interrelated. So there's a high degree of correlation between the different components, or among the different components, because all of them are correlated. And so that's not a very good tool for data compression. As you saw with my camera over here, we were able to say, I want high resolution, low, fine, basic, core. Well, I do that by throwing out some of the components so they don't all have to be saved. Well, if they're all correlated and you throw some out, you mess up the others. So it's not, Fourier analysis doesn't work very well for digital cameras where the money is at these days. So we have to do something else. Likewise, we don't want to recompute the Fourier components each time you change the analysis, so we need a more data or model-independent, data-driven, model-independent analysis, and that's what wavelets do. So let's get on and begin to look at wavelets. Please look at slide 11. Now here, as we'll try to do in this first lecture, we'll try to give you a basic understanding of wavelets. Some of you may not feel comfortable understanding something until you actually can run the code. We'll do that next time. Okay? This time we're just talking about the basics, because once you get the basics down, then the mathematics is just accounting. It's easy to follow. Okay? It's not a mathematical subject. The basic idea is what's new and what's good. So here we see 3 wavelets for your enjoyment. Yellow, gray, and sort of muddy pink color. Okay? And one of them looks like a Mexican hat. It's a Gaussian with some wings on it. The other is obviously just a square wave going up and going down. And then a pulse, a nice little wiggly pulse. Okay? So this is what we'll use. This is the basis for extending Fourier analysis, the basis of wavelets. So wavelets are fairly recent. You'll find it in some textbooks, but not many, ours for sure, and then some more advanced text. But it's had extensive applications in recent times. And it's had applications in physics, it's had applications in geology, in exploration, in seismic analysis of earthquakes. It's even been used in brainwave analysis, biology as well. Anytime we want to localize the signal and know when it's happening, get more information than we can with Fourier analysis, we'll use wavelet analysis. It has an extra degree of freedom over Fourier analysis, which makes it more complicated to do by hand, but it's just perfect on the computer. So it's very good. So these are wavelets. These are 3 different wavelets, and what we can see is, well, all of them do something in common. They all oscillate. So if we have a 0 line drawn someplace like here, let's say, or here, then they're all oscillating about that line. Okay? And so all functions oscillate. Their functional form are obviously very different. It doesn't matter. These are all called mother wavelets because they'll generate daughters of various sizes and same shape, and they'll be the basis of a wavelet expansion. So in a nutshell, we are now going to expand any arbitrary signal, but particularly one that varies in time, in terms of wavelet bases. So these will be our basis function, these little wave packets. Okay? They're called wavelets, the lits meaning small, like ET in pack or packet. They could be called likewise wave packet analysis, but wavelets are cuter and haven't been used before, so that's it. What else we see in common for each of these wavelets is that they all have a finite period over which they exist in time. That's where we get the time resolution from. And as we'll see, each can be centered at a different time. This is at 0. These are all centered at 0. We'll move them around. Okay, that's not a restriction. So let's talk about wave packets in general before we get on to wavelets in analysis. So look now at slide 16. And on this slide you see two things. You see a wave packet on the left, and this is just a pulse. So it's a pulse here that has finite time over which it exists, and when it exists, it's just a simple sine wave. Okay? And what it generates in Fourier space is a Fourier transform, which also has a simple form, a nice pulse in the middle, and then oscillates out to all time. So specifically, it's a sine wave for n periods. N is some arbitrary number here. Here it's 1, 2, let's see. This is 1 period, 2 periods, 3, 4. This is 5 periods. Okay? And each period is some time t. So we know how long it is in time. It has some frequency value as well. So the time uncertainty, it's not quite uncertainty, but the width in time is n times a period, n 2 pi over omega. And as we'll see, look in the textbook where we actually give you the analytic form for this Fourier transform. The width here in transform space is approximately omega 0 over n. Okay. So what we see here is something interesting. We see that we have a function which is basically a sine wave, and yet its Fourier transform has not one component. It has mainly this one big component, but it has lots of wiggles out here. Why so much? Well, that's what these arrows indicate. We have a corner here and another corner negative time in which the function is cut off. Well, the way you get a cutoff in time space is by adding lots of frequencies together. Corners require lots of little frequencies. And these are those lots of little frequencies. Okay? So the sharp edges here is what gives us these higher components, but nevertheless, it's basically finite width in time, finite width in space. Okay? So now let's look at this, the mathematics a little bit more. Look at the equation in the textbook if you really want to go through it in detail. And we try to derive a general truth from this one example. So it's called the uncertainty principle. And the uncertainty principle is really the basic theory behind wavelet compression, digital analysis of wavelets. So it's a general truth. We get that from our one example. So if we look here at the width of the Fourier transform and ask, what's the width of the Fourier transform? Well, if we look closely, we'll say, why don't we say it's where the function goes through 0 on the left, the function goes through 0 on the right, so that is approximately what we call delta omega. Okay? So we can look, when does that occur? Well, that occurs when omega minus omega 0 over omega 0, and this comes from the analytic form, is plus or minus 1 over n. Ah, that makes sense, because if we said, let's make the function we have here extend larger and larger, more and more cycles, n would get larger and larger, then the frequency spread becomes less and less. It all gets narrowed down till when n approaches infinity, if we have a pure sine wave, then we would have only one frequency. So here we get our expression, the width in frequency space is the basic frequency divided by n. That's just what we were saying. And so if we look at n cycles, which is what we have in our signal here, we have n cycles of a sine wave, that means the uncertainty or the width in time is just n periods. And if we, lo and behold, multiply the number, the width in time by the width in space, we get what's known as the uncertainty principle. Okay? So the width in time times the width in space is always greater than 2 pi. In quantum mechanics, the Heisenberg uncertainty principle says that the uncertainty in the position of a particle times the uncertainty in the momentum of a particle is always greater than 2 pi times h bar. But the basic idea doesn't come from quantum mechanics. It comes from any time you have two spaces related by a transform, or a Fourier transform in particular. They must obey this relation. So it's a general truth. Quantum mechanics is just one example. It's wonderful to use this now as the basis of all wavelet analysis. So before we do that, let's go on and have you run into the lab or do it on your computer at home or even on a desktop. Let's do some exercises to give you a feel for wave packets. I mean, wave packets is one of these subjects, like in quantum mechanics, where we always start off with wave packets because particles really are wave packets. But then we never look at them again because you need a computer to do the analysis, and everybody does the analysis analytically, by and large. This is a computational physics class. We'll do the real analysis. So you go home. Well, I say we, but it's you. You go home, look at these three wave packets. So we have y1, a pure Gaussian, y2, a Gaussian times an oscillatory sine function, and y3, a Gaussian times a polynomial. They're all pretty symmetric in one way or another, so it makes this pretty easily. What we want you to do is to see how well the uncertainty principle applies for each of these cases, and to give you a feel of what the width and time, width and frequency means. So estimate first for each of these three wave packets the width and time delta t. Fine. A good measure of that is the full width at half maximum. In other words, when the signal has fallen to half of its largest value, how wide is it on both sides at that point? The full width at half maximum. And if it oscillates, just use the absolute value. Do the same thing now. Evaluate the Fourier transform for each of these cases, either analytically or numerically, whichever you feel most comfortable or most proficient at. And then, once you have the Fourier transform, analyze what its frequency width is, or its uncertainty in frequency space, delta omega, for the Fourier transform. Again, the full width at half maximum is a good measure of that. And then determine how well the uncertainty principle holds for each of these three cases. In other words, multiply your width in space, or time, times your width in frequency, and it should be 2 pi times some constant. Determine what the constant is. Any number greater than 1 is okay, because we think it should be greater than some 2 pi. If c is less than 1, then go back and see, whether you made a mistake. You should find c greater than 1. So do the exercises. Then next time we'll come back and we'll start doing the Fourier analysis in more detail. Bye-bye.